Welcome. All right, the goal of this video is to discuss the normal distribution. And what we are hoping to do in this video within under 10 minutes is to learn to review the empirical rule, to kind of understand the properties of a normal distribution, how to convert to a standard normal distribution, and solve some problems using applications of the normal distribution, and then finally create a normal probability plot. So let's take a quick look at our first thing, and that is the empirical rule. All right, the empirical rule said if you have something that is bell-shaped, okay, and you have a mean in the middle, why? Because it's bell-shaped. So your mean is of this population is going to be in the middle. And if you were to go one standard deviation this way and one the other direction, then this would contain 68%. Well, mine's not very great right there, is it? 68% of the data. And because this is symmetrical, that means there's 34% one below and 34% above, right? And then it says if you go two standard deviations, right, this gives you a total of 95% of all the data. Okay. Now let's do some real quick math here. 95 minus 68. Well, remember this, how we have to borrow. All right, that's 7. And then 8 is 27. If I divide that by 2, and doesn't come in evenly, is 13.5. So this means that there's 13.5% of the data here and 13.5% of the data here, right? All right, and then if you go 3 standard deviations away, according to the empirical rule, you have almost all the data. You have 99.7% of the data. So if we do some math there, that means we have 0.3% on the data outside, right? It also means like if I have 99.7 minus 95, that means there's 4.7, right, left over in these little holes. And if I divide that by 2, I'm going to get 2.35. So it's 2.35% here, 2.35% here. And since there's 0.3 left over on the outside, I divide that by 2, I get 0.015. So 1.5%. Oh, sorry, 0.15%, not 1.5, that'd be 3%. This is 0.3%. Let's make sure I write that clearly. So 0.15% here, less than 0.25% right there, right? This is the empirical rule, and this works for anything that is bell-shaped, also known as normal in distribution, right? So this is the empirical rule. It is a rough kind of guide for us to kind of understand how this distribution works and how the data falls very close around the mean. Most of the data is surrounded right here around the mean, right in here, just one standard deviation away, right? That's the empirical rule. Right. Now, let's talk, just note, right, like a uniform distribution, sorry, that's not what we wanted. One second, please. A uniform distribution is something that looks like this, right? My mean is here, and it's uniform. You're not going to find, like if I were to divide this into, three standard deviation or 3 chunks away, right? If I were to divide this into 3 chunks, right here, I'm only going to have a third, just 30%. Definitely not 68%, because this is uniform. If I go 3 standard deviations away, I'm going to have the same if I go 1 standard deviation away, because it is a uniform distribution. So just keep in mind that this is special for the normal curve. The normal curve is key to making the empirical rule and what we're talking about for a good chunk of this term to work, right? There are lots of different types of distributions. You could have a triangular distribution where most of the data is up front, and then it goes down, 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 right? Like that. You can have an exponential distribution where it looks something like this to a certain point, right? So there's lots of different types of distributions you can have. But what we're going to spend most of our time with is something that looks normal. This is a normal distribution. Some properties of the normal distribution is that it is symmetric around the mean, right? It's symmetric around the mean. So if I go the same distance this way and the same distance this way, these will have the same height. Okay? It's symmetric. I could fold it over about the mean and it would match perfectly. The important property of that. All right. So now we can start using the normal distribution to answer certain questions. And I'm going to pull a couple questions right off kind of your homework to talk about what we're doing this, and that will get into how we go about using this. I don't know if you guys remember from like high school geometry about your circles, right? Yeah, you can have that's not a circle. Sometimes I forget where the undo button is here. There we go. Right. So when you have circles, again, not a circle. Let's see if we can get this to draw a circle for us. All right. Let's see. There we go. Okay, when you have a circle, all your circles are similar, right? They're all have the exact same shape, regardless of the size, right? Big ones, small ones. Oh, not a circle again. So that's not a circle, that's oval. So you have like all of these. If it's a circle, it's like perfectly round circle. When you have a circle that has a radius of 1, we call that a unit circle. Same things happen with normal curves because they're all symmetric around the mean. They all have the same shape. Right? If you have every normal curve, just like every circle that's similar, can be transformed into a unit circle. So every normal curve can be transformed into what we call a standard normal curve. And a standard normal curve has a mean that's at 0 and a standard deviation of 1. Right? This could have a mean and a standard deviation at anything. But a standard normal curve always has the 2 parameters, mean at 0, standard deviation of 1. Mean at 0, standard deviation of 1 gives you a standard normal curve. Now let's say I had a mean at 5 and a standard deviation at 2. And I wanted to know what this point, let's say what 6 was. I could map 6 onto a standard normal curve, right, by looking at the z-score. The z-score, if you remember from before, is the data point minus the mean divided by the standard deviation. Right? So if I take that, that's 1/2. That's our z-score. Okay? Again, a z-score, as we learned last term, is the data point minus the mean divided by the standard deviation. This tells us how many standard deviations away from the mean we are. In a standard normal curve, because the standard deviation is 1, this would just plot to 1/2. 6 on this curve is the same relative distance away from 5 as 1/2 is on this curve. And there is the same area in between these two things. Has the same area. Same area between 5 and 6 with a standard deviation of 2 as in 0 to 1/2 on a standard normal curve. Okay? So you use the z-score. As such, when we talk about distributions that have, when we talk about distributions that have any mean and any standard deviation, we'll usually refer to their data points as x, their random variables as x, capital X. When we talk about a standard normal curve, we'll usually refer to theirs as capital Z, those random variables as z. So a lot of what we will spend our time doing is asking questions about how likely is it that I'm going to have something happen. So let's talk about probability for a continuous area real quick. Right? Let's say I'm rolling a dice, and just probability, quick review. I'm rolling a dice, and I say, what's the probability of getting a 3? I know that there are 6 things on a dice. One of them is a 3, so that's 1 out of 6 probability. Pretty simple when the things are discrete. There's not a 1.5 and 2.5 and a 2.33 and a 2.3447 and a 2.8889 on a dice. So it's pretty easy. Count 1 over the count. Let's say I'm playing darts, right? And here's my bullseye right here. I want to know what's the probability of me hitting my bullseye. Right? Well, then I have to look at the area of the whole thing, the area of this whole thing, and then take a look at the area of success here. So it's the area of the bullseye divided by the area of the whole target. And that's the probability of me getting a bullseye. All right, I have to start talking about area. Same thing is going to happen when we are talking about our normal curves. Right? We are going to really be looking at area. Right? Let's say, let's say you have a mid-sized company, and the number of phone calls each day of the 12 receptionists is bell-shaped with a mean of 63 and a standard deviation of 5. So I have this bell-shaped curve, and these guys are taking in 63 calls a day with a standard deviation of 5 calls, right? And if I were to just use the empirical rule here, if I go up to 68 and down 5, right? Down 5 from 63 would be 58. I would know that 63% of all number of calls are in this range. Mm-hmm. And then if I go down another 5 to 53, and up another 5 to 73, I would know that 95% of all the calls are in this range. If I go up another 5 to 78, and down another 5 to 48, I would know that 99.7% of all volume of calls are in this range. So using this information, I would say, how likely is it that on a day that these guys have 59 calls? Pretty likely. It's in this big range here. Right? How likely is it? Well, 59, I should say, 59 or more. Like that's a typical number, right? These numbers in here are going to be relatively typical. The numbers here are relatively typical. What if I said, how likely is it that they get 47 or less calls? Very unlikely, right? 79 or more calls, very unlikely. So this gives us an idea of what is typical. The question that is proposed is, what's the approximate percentage of daily calls numbering between 48 and 78? Well, look at that. 99.7% of all daily calls are in between 48 and 78. Right? What if I asked between 58 and 68? 68%. What if I said 63 and 68? 34%. What if I said 68 and 73? 13.5%. Right? So they have this. This is just using the empirical rule to get an idea of how many calls based on this distribution. Right? So remember that this was 34 and this was 13.5 and this was 2.35 and this was 0.15. And if you notice, right, that makes sense. 72 is right in here. And if I add those together, I get 2.5, and then I have this little extra here, so I get 3.6, right? What if I wanted to be more specific, using the same example, where I had a mean of daily calls of 63 and a standard deviation of 5. And I said, you know, I want to know the exact probability of getting 72 calls or more. Now, I'm going to say just exactly 72 because the chances of getting 72 exactly are infinitesimally small. And you're like, well, 72 is kind of a common number. Yeah, it is, but exactly 72 when there are infinitely many possibilities would be very, very unlikely, right? Now, calls is kind of a discrete thing that we're counting, but you get the idea. All right, so 72 or more. I am looking for the area under the curve that matches this right here. And I want to find that exactly. Now, those of you who have taken a calculus class, well, I didn't know you need calculus for this. You don't, and I'll tell you why. But those of you who have taken a calculus class know that this would be the integral from 72 to infinity of this function right here, which actually has a function. It's 1 over 2 pi. Is it 1 over 2 pi mu e to the x minus mu squared all over standard deviation? 1 over 2 pi. So there's something here. I've got to double check on this. But rest assured you don't need this. Because a long time ago, mathematicians were like, we use this all the time. We should make some tables. And they had paper tables. And then technology happened. And the tables were not as good as the technology because the technology was so much more precise. So we just use our calculators for this now. And the way that we do that is we are going to go to our calculator. And I'm using the XI-84 for this example. And we're going to find the distribution button. Okay. And we're looking for the distribution function that is called normal CDF. So on your calculator, you would hit the second button and then the vars, which above says distribution. So you're going to the distributions. And then you're looking for the normal CDF, which is number 2. And this stands for cumulative density function. Cumulative because we're going to add everything up from 72 on to infinity. Okay? If you're using PDF, it's probability density function, and that would tell you the length of this height right here, which is kind of useless for us in practical terms. So we're not going to use PDF for continuous distributions. But we're going to use this CDF, which is number 2. It's going to say, hey, what's the lower limit? I look here and I say, well, our lower limit is 72. So I put 72 in. what's the upper limit? I go up to infinity, but there's not an infinity button. So I'm just gonna put in a really big number here, put a 1 with a bunch of zeros. Once you get so far up, it is like statistically insignificant. So just put a whole bunch of 1s with some zeros there, great. If you have an 89, you can actually put in the infinity there, but that's fine. Ask what my mean is, I'm gonna say 63. Ask what my standard deviation is, that's given in the problem, that's 5. And I'm gonna hit enter twice. And this is gonna tell me that 0.0359. So roughly 3.6% of my calls are going to be 72, or days are going to be 72 calls or more. Let's look back. So this feels right. Our answer feels right. And it's really important to think about, oh, does my answer feel right? Does my answer feel like this could be the correct answer? Especially like if they were to say, what if they say, if I were to get a number that was like 0.57, if I had typed it in wrong and got 0.57, I could look at this and go, how could that be more than 50, which is 57%? How could this be more than half of the data when it's above the mean? If it's going to be more than half the data, then the number would have to be somewhere below the mean going this way, right? That would represent more than half the data, right? This could not be more than half the data. So I should always keep in mind, like, what does the picture look like? How could this feel right? The other thing that we're going to do in this homework tonight, and I'm going to kind of wrap this up because I don't want this video to be super long, is this week, you're going to be talking about going the other way, right? Let's say I have 63% of the calls, right? And a standard deviation of 5. And I ask the question, hey, what's a slow day look like? Okay. What's a slow day look like? Could I mark slow days? And let's say slow days for me are going to be bottom 10%. Anything that's in this bottom 10% right here, I'm going to consider that a slow day. And I'm going to mark and see, like, this bottom 10% slow day. So I'm going to kind of mark, maybe I'm looking like, are certain days more slow than other days? Like, if it's in the bottom 10%, I'm going to say that's a slow day. I'm going to mark, and maybe every Thursday is a slow day. And maybe that's a day I can start giving people some additional tests to do or some additional time off, because Thursdays typically are slow days, but they have to be in this bottom 10% for me to classify it as a slow day. So I want to know what the cutoff number is here. So I'm going the opposite direction. Instead of having a cutoff and saying, what's the probability of this happening? I have a percent and I'm asking, what's my cutoff value? And to do this, we're going to go into that same distribution menu on our calculator. And I'm going to choose inverse normal. Okay. So this is, right, the inverse function of the normal CDF. So I'm going to go inverse normal, which is number 3. And it's going to ask me, hey, what's the area that you're looking for? I'm looking for the 10%. So I'm going to put 0.10. My mean, again, once my mean, which is 63, and my standard deviation, which is 5. And then it says, what tail do you want? Do you want the top 10% up here on the right, which would be over here? Do you want that 10%? Do you want the 10% on the left, which is what we do want? Or do you want, they give you another option, this middle 10% here, surrounded around the center. Those are the 3 options that the TI 84 Plus gives you. Please note, Excel, Minitab, and older TIs only give you the left option. So if I wanted the right 10%, then I would need to type in 90%, the bottom 90%, to get the top 10%, because those two share a number, right? So I want this left, so I'm going to go here, and I'm going to hit paste, enter, and this number is 56.6. So anytime I got 56 calls or less, I would say it's a slow day. I'm only getting 10% of my calls. All right, so hopefully that is helpful as you go through. Again, I don't want to make these lectures super long, so let me know as you go through the week what questions you have, and I look forward to talking to you soon. Thanks, bye.